Welcome back to our last lesson in the unit on permutations. This is lesson 4. We're going to look at permutations with some identical items. Now we've selectively chosen words for you like trickle and potluck where there aren't any repeated letters. And we've asked you to arrange n distinct items or r of the n distinct items, right? But I mean, what do you do if some of the items are not distinct, meaning you can't tell the difference between them when you look at them? What happens to all of our permutations when some items are identical? Okay, so we're going to answer that question. Let's just take a moment, and what I'd like you to do is list all the different permutations of the word LOL. Okay, so first of all, let's imagine that we can use a subscript, like capital L sub 1 and capital L sub 2, to differentiate between the two L's. So let's say you've got Scrabble tiles and one has a scratch on it, so you can tell the difference between them. Okay, so take a moment.
Take a moment now.
Think of, literally write down LOL, LLO, like write down all the different ways that you could write out LOL if you can tell the difference between those two L's. Okay, so pause and do that.
Okay.
Now,
so here's what we
come
get.
Back. Yep.
So here's what we get. L1 O L2, L2 O L1. L1 L2 O, L2 L1 O, O L1 L2, O L2 L1.
Yeah.
Right, so we chose a method where we're going to put L1 first, and then put the O in the middle, and then put the O at the end, and then put the O. Really, it was just a method to create a list. So this is a good example of creating a list to organize our counting.
Yeah.
All right, no problem.
So
how
6
many of
different
them?
Ways.
There's 6 of them.
Yeah.
Okay. Now,
and this makes sense, Mr. Jackson, because we were arranging 3 distinct items in 3 spots, which is 3 factorial, right?
Yeah. Okay, what if you can't use a subscript to differentiate between the two L's?
What if your Scrabble tile doesn't have a scratch? Those two L's look the same.
They're indistinguishable. How many different ways can you arrange those letters now? And if you press pause and you try this, and then come back, what you're going to get is you're going to get LOL, LLO, or OLL. That's it. Because OLL with no subscript is the same as OLL. There's no way to tell between those two L's. So you get 3 different ways. Okay.
All right.
How many ways can you arrange 2 distinct items?
Well, if there's 2 items and I'm arranging them in 2 spots, then there's 2 factorial ways to arrange 2 distinct items.
Okay.
Okay.
So,
Now,
I wonder.
We have a relationship here. The 6 and the 3. The 6 we got when we could tell the difference between them, and the 3 that we got when we couldn't tell the difference between them. And we know that there's 2 items that were identical, and there's 2 factorial ways to arrange 2 items.
So 6 divided by 2 factorial.
All right.
I wonder.
Let's try something out.
Okay. So, how many distinguishable 4-letter arrangements? So how many permutations, 4 letters taken 4 at a time, are there for each of the following words? Mace, M-A-S-E, all identical.
Sorry.
How many?
Non-identical.
Excuse me. None are identical.
All the M-A-S-E, you can't tell the difference between them. They look identical. No, they're all unique.
They're all unique.
Yep.
And so how many different permutations are there of these 4 letters? And again, create a list.
Yeah. Or if you don't want to create a list.
If you don't want to create a list, you can say, oh, well, 4 letters, no repeated letters. It's 4 factorial.
Yeah, 4 letters, 4 spots.
24 different ways of doing it.
Yeah, that would take you a while to write out.
Yeah.
It's okay.
Okay, so now we've got mass, which is a little bit different than mace because we got 4 letters, but 2 of them are identical. So now how many can we arrange these into? Well, this is what we got. We got M-A-S-S, M-S-S-A, and so on and so forth. And as you'll notice, this is all that we can do because we can't tell the difference between those 2 S's.
Yeah.
Okay. So there are, of course, 12 arrangements. There's 4 letters, but 2 of them are the same. Yeah. So there's only 12 ways that we can arrange these. Yeah. What about SAS? S-A-S-S.
But I want to think a little bit about that last example.
Okay.
Right? Because essentially what we're saying is that 4 letters arranged in 4 spots should be 4 factorial, or 24. But 2 of them look the same as each other, and we've divided out the ways of arranging the two that look the
Yeah.
same.
Okay.
So 24 divided by 2 factorial
Yeah.
is 12. It is, I mean, we've written it all out, but if we use some of our thinking that we did in example 1, our little
Okay.
then we can see, oh, 24, which is 4 factorial, divided by 2 factorial, which is the number that are the same, gives us the same number as when we scratched it out by hand.
Okay.
Can we do an experiment
Then with
SAS?
this. So we have 4 factorial. We'd have 4 factorial ways of arranging these 4 letters, but 3 of them are identical. So here we got 4 factorial. They're all unique.
Yep.
We got 4 factorial divided by 2 factorial because we had 2 identical letters.
Yep.
Here, solution, guess?
Guessing
4 factorial divided by 3 factorial because there are 3 identical items. Yep. So basically when we do this, we get SASS, SSS, SSAS, and SSSA.
Yep. 4.
There's 4 letters.
How do you get 4? Using...
Yeah.
All right, let's just see. Let's just see. So if we did our 4 factorial, which is 24, over 3 factorial, which is 321, which is 6, 24 divided by 6 is 4. So we've hit on a little pattern here, yep, which is however many letters you're arranging, that's your numerator.
Yep.
But your denominator, you have to divide out the ones your eyes can't tell the difference between.
Yes, exactly.
Okay?
So let's formalize this.
So it becomes fewer distinguishable permutations. Yep. That's the whole point of it. If you can't tell the difference between them, they look the same as all the other ones.
Mm-hmm.
Yeah.
So here it is, permutations with some identical items. The number of permutations of a set of n objects containing A identical items of one type, B identical objects of another type, C identical objects of a third type, and so on, is simply n factorial divided by A factorial, B factorial, C factorial, yep, and so on and so forth. So let's take a look. We got some words here, some Southern Ontario words.
Let's take the word Waterloo. So we say, okay, well, Waterloo, that's 8 letters. I do see there's 2 O's there, so that O is repeated twice. And they're all capitalized, so we're going to assume that the O's are indistinguishable. It means I can't tell the difference between them. So 8 letters in 8 spots is 8 factorial. We're going to divide out the indistinguishable permutations because we can't tell differences. You switch those O's around and I looked away and looked back, I wouldn't know you switched them around. So 8 factorial divided by 2 factorial gives us 40,320 divided by 2 times 1, which is 20,160. So there's 20,160 distinguishable permutations of the word Waterloo because that O is repeated twice. Yeah.
What about Toronto? It's a little bit different.
Well, what do we got there?
Well, we got the 3 O's.
Yeah.
That's for sure.
Yeah.
We also have 2
T's.
T's. So this is one where we've got different types of indistinguishable items.
Yeah. So can we just divide by 5 factorial? Because there's 3 O's and 2 T's.
We cannot.
Uh-oh.
What we need to do is we need to say, okay, well, there's 7 letters in the word. So 7 factorial. And we need to divide by 3 factorial, which corresponds to the O's, and 2 factorial, which corresponds to the 2 T's. And when we do this, we get 5,040 divided by 6 times 2. So there's 420 ways of arranging the letters in the word Toronto. Distinguishable ways.
Distinguishable ways, okay, which significantly reduces the number of ways of arranging 7 items in 7 spots, right? Without any indistinguishable items, it would be 5,040. All right, Mississauga. Just pause it for a second and try this one out on your own. And then come back.
All right, so here we are. Hopefully you've tried this out on your own. We have a couple of S's here. We've actually got a quadruplet of S's. We got a pair of I's. We got a pair of A's. So there are 11 letters in the word Mississauga. 4 S's corresponding to 4 factorial. 2 I's corresponding to 2 factorial. And 2 A's corresponding to another 2 factorial.
Sure.
So when we do this, of course, 11 factorial is 39,960,800. We divide by 24 and 2 and another 2, and we get 415,800 distinguishable ways of arranging the letters in the word Mississauga.
Yeah.
Okay. Now, here's a question about your friends.
Yep, that's right. That's right. Okay. So I have 2 parrots, Archie and Skipper. They know how to do a couple of tricks, okay? They're not fancy birds, but they know how to do a few things well. Let's say at our last training session, they hopped 4 times, they turned around 2 times, they shook hands 3 times, and they gave 2 kisses, okay? In how many ways could this session have occurred? Now, when you see a question like this, the implication is that there is a series of events that happen, just like a series of letters to be arranged, but that some of the events are not really distinguishable from the other. Like one hop looks like the other hop, right? Not like they hop on a different foot or something, right? And that turning around looks the same as the other turning around. So we're looking at some indistinguishable elements in amongst a series of actions here. Okay. So how do we figure out what my birds were up to?
Okay, well, we got 11 tricks that we're going to distribute, but a couple of them are identical.
Okay.
So 11 tricks is going to give us 11 factorial, and that's going to be our numerator. Right? However, in the denominator, we've got 4 factorial hops, we've got 2 factorial handshakes, or sorry, I guess 2 factorial turnarounds. We've got 3 factorial handshakes, and we've got 2 factorial kisses. And so when we multiply and then divide, we've got 69,300 different ways that this session could have occurred, given that the hops, the turnarounds, the shaking hands, and the kisses are indistinguishable.
Kind of look the same. Yep, that's right. All right, so now this is where it gets good, people. Not only do you have some indistinguishable elements, but now we're going to start stacking restrictions on top of that, okay? So what if we want to know how many permutations of the word Tennessee, which has some indistinguishable elements, do not start with the letter N? So we do not want either of those 2 N's at the beginning of the word Tennessee, which means they could be anywhere else, but they can't be first. So they could be second, they could be third, they could be fourth, they could be fifth, sixth, seventh, eighth, ninth. That's a lot of options for where they could be. So that's a lot of direct cases, Mr. Jackson.
However, the indirect method may be our friend in this case.
So maybe we do want it to start with N, and then we'll subtract it out.
So we're going to use an indirect method. Absolutely, we're going to use an indirect method. And what our indirect method is going to be is, hey, let's find the total number of permutations of the word Tennessee. And we're going to subtract from that the number of ways where N is the first letter.
Yeah, let's put it first.
Put it first.
Just put it there.
Then we'll have the number of ways that it does not start with the letter N. Okay, so here we go. So first of all, how many total? Well, there's 9 letters. And what we're going to do is we're going to divide by the repeaters. So we have 4 E's, we have 2 N's, and we have 2 S's. And so we divide 9 factorial by 4 factorial, by 2 factorial, and by another 2 factorial. And what we end up with is 3,780 different ways of arranging those into distinguishable permutations.
Without any other restrictions. Okay.
All right, so let's put N first. So how many different permutations start with the letter N?
Okay.
Well, here we've got N first.
But aren't there 2 N's?
There are 2 N's. But as soon as we lock this N into place at the start of the line, we've made it a distinguishable character. We've made it distinguishable from the other N because we've put it in its spot. Now,
so the other N is now no longer repeated.
Exactly.
Once we've put an N there, it doesn't matter which N we put there because they look the same as each other.
Because they look the same. So
but once we put it there, it's kind of out of the race.
It's out of the race. So now the other N just becomes another regular letter. So now we have 8 letters to choose from and 8 spots to fill. So that's 8 factorial, but we still have the 4 factorial E's and the 2 factorial S's. N is no longer repeated.
Notice the other 2 factorial that was in our total is not there, and that's because we've already pulled one of the N's out.
Exactly.
Okay.
We've already pulled it out. So this yields 840 unique permutations with N at the start. Okay. So really, if we want to find out the answer, then we take 3,780 and we subtract the 840 from it, giving us 2,940 distinguishable permutations of the word Tennessee, not starting with the letter N. And of course, basically, we can summarize this with a therefore statement.